Hi guys, welcome to another one of DOWLATH Revision series lectures, and we are at number 12, and today I've decided to extrapolate the concept of Newton's second law to include an inclined plane. So if you look at this diagram, we'll just consider the typical horizontal body. So normally you would have along the horizontal plane a force applied, and once the object is moving, let's say it's being pulled to the right by a force F, then you would have a drag force because the surface is not completely smooth, so you would have some degree of friction, so you would have a drag or frictional force exerted opposing the motion. So the resultant of those two forces, right, the F minus the drag, is what is equal, which is the resultant force according to Newton's second law. Is that we say the body moves horizontally, it means that there is a balance of forces on the vertical plane. And normally you would have the weight pushing down, and then you would have your reaction force, right? Because it's like you're considering an application now of Newton's third law, where you have the weight of the body pushing down on the surface and the surface exerting an equal and opposite force. And that force is what we call a reaction force or a normal. So imagine now I take this entire apparatus and I tilt it at some angle theta. Do you think that the weight will have an effect along the horizontal plane? So it's quite interesting because if you consider the surface completely horizontal, then only your horizontal forces will act. That is your force and your drag. So you will not consider the weight because the weight is along the vertical plane, which is perpendicular to the horizontal plane. However, if we take that surface and we incline it at an angle, we are seeing now that the weight will have an effect on the forces along the plane. So this is an example of an inclined plane, and it is a variation to your normal horizontal surface, because now we don't consider forces simply along the horizontal or vertical planes, but we consider the forces perpendicular to the plane and parallel to the plane. Now, in this concept, we're seeing that we would still have our reaction force here, but it becomes now perpendicular to our surface, and the weight would have acted totally down, vertically down. And because we have elevated the plane to some angle, we would have two components to the weight. And that is a concept that we term resolving a force. Now, when you have a force acting at an angle to the plane, there are two components to that force. In the case specifically of an inclined plane, you will have one component of that force here being perpendicular to the plane and one being parallel. For an inclined plane, we are seeing that the component which is perpendicular is equal to the weight by cos of the angle. So if this angle was 30 degrees, it would have been cos of 30 degrees multiplied by the weight. If we were considering this component of the weight along the plane, along the surface, it will be, let's say, sine of 30 by the weight. Now, sine of 30 is a half, right? So it means that the components are actually less than the weight itself, right? But the purpose of the components is that it follows from the general rule of thumb that if you have a vector at an angle, then that vector can be resolved along two directions. In the case of an inclined plane, it is perpendicular to the plane. So your perpendicular axes will be like this, perpendicular to the plane, or it will be parallel to the plane. Why I'm telling you this is that you could extrapolate your knowledge of Newton's second law to consider objects along a plane. So here, I had mentioned to you that once you're talking about a completely horizontal surface, then the force minus the drag along that plane will be equal to the resultant force. And I will not have the weight affecting the motion or affecting the magnitude of the resultant force. But from the time you have that same system, right, of forces now inclined at an angle, we are seeing that, guess what? You will have the weight affecting the resultant force along the plane. And the answer is why? The answer is when you have that system being inclined at an angle, we are seeing that there is a component now of the weight that acts along the surface of the plane. So now, if you wanted to get the resultant force, it would be the weight, well, the force up minus the W sine theta. W sine theta always acts downwards. That's a fixed direction. And of course, if I had to factor in drag, if I'm pulling my object up, I would also have my drag force, which acts along the plane, acting down. So it is now the combination of the force, the drag, and the component of the weight, W sine theta, that will give me my resultant force. So if we do a question, so I have a 5 kilograms, so G will be 10 obviously. I have a 5 kilogram body being pulled or pushed up a slope, and I'm going to consider the slope to be smooth. So in this context here, I am not considering any drag because I'm considering the surface of the plane to be smooth. So in a question, if you are told that the surface of the plane is completely smooth, then you are not considering a drag force. So now you would have 100 newtons pushing the body up, and remember what component of the weight acts down? We have a fixed expression, which is W sine of theta. That does not change, it always acts downward. The only other force you would have included here is the drag, had there been any friction. But we are ignoring that for simplicity in this question, because I really wanted you to see the effect of the weight once you incline a surface. So now you have 100 minus W sine theta, and this will be 100 minus, and W is mg, so it would have been 5 by 10, which is 50, by sine of the angle, which is 30. So this works out here to be 25. So then the net resultant force along the plane will be equal to 100 minus 25, which is 75 newtons.